Şirketlerin son içerisinde kalanlık. Что разница? Seam welded pipe и gear seam welded pipe. Do you know what the difference between seam welded pipe and gear welded pipe?
The seam means you have to hold the plate. So this is the plate.
Yeah.
And you weld it. Okay? And so this is where it meets. This is where you weld it around.
This is what? This is seam.
Yeah, that is
And gear? This is seam, yeah?
Yeah, we will be the one, the line of welding gears. Very much. Yeah. Because gears, welding is between, I mean, two joints and the welding.
Seam level. Gears welded. Кольцо, чтобы он обнажировал. Это что, gears? Yeah, gears welded. Gears welded is here.
already circumference.
Кольцо welded. Yeah, будет кольцо канал, а хуже seam welded. Buildability.
Okay, so I gather that Dr. Euler finished the last lecture with some words about ductile fracture. Basically, when you have a steel which is reasonably well prepared, the quality of the steel, which is related to the amount of impurities were in the steel, can have a big effect on fracture. And the example that you can see here is a couple of steels with the same basic composition, but one of them has a little bit more sulfur in it than the other one, and it's the one at the bottom that has more sulfur. And in the primary steel making process, we add manganese to the steel as a deoxidant, but it also reacts with the sulfur to form manganese sulfide. And manganese sulfide is a little inclusion, a little particle in the steel. So in the top case, you can see the grey, which is effectively the steel in this polished cross section, and there are a few dark spots. And those are the manganese sulfide inclusions. And when you've got a few dark spots and lots of spaces between them, that's good. And then we tend to have a quite tough steel. So on the top of the ductile brittle transition, the shelf has a relatively high energy, and that's a good ductile steel. If there's a bit more sulfur in the steel, the manganese reacts more. There's more of those inclusions. When the steel is rolled, which it's done for making the pipe, those inclusions tend to form little lines. And then you see these large defects, and you get a very low ductile shelf energy in that particular case. So the toughness has gone down. Small amounts of sulfur can have a big difference because of that. And why is that happening? Well, we're getting these elongated inclusions, and they're brittle, and they're being connected up by cracks, a bit like the perforations in a piece of toilet paper. You get preferential crack path, which is easy to follow. And so that's why you get a lower energy. And this steel, of course, is not as good as the top steel for use of the pipeline. So we want to be able to just monitor the basic materials that we're using to make our pipe from. So we don't have to go to full pipe manufacture. And that's why we tend to use Sharpie tests, which are smaller test pieces and easier to measure the big pipe sections.
So,
Yep.
so in steel 2, the picture, the image which you showed,
Yeah.
that's the microscopic level, right?
Right. Well, yeah. Those inclusions there are microns in size. So, in order to look at that, you would cut a piece of steel, you'd polish it to a mirror finish, and because there's a difference in reflectivity between the steel and the inclusion, you can see them in the mirror finished case. If you want to see the steel microstructure, you then chemically etch it, but you don't need to do that to see these inclusions. So yeah, these are very small. You wouldn't. These are not big defects. These are, as I say, micron-sized defects, and that's really what you need. So why is this important? Well, we got some highly ductile failures in the US in the 1960s, and we say the words there long running, and I've put long running not because they lasted a long time, but because one defect crack produced a crack that unzipped a pipeline for a kilometre or more. So one defect, and then the pipe responds by propagating that crack, and effectively you destroy a large proportion of the pipe. And this was really related to the quality of the metal that was being produced. So the stored strain energy in the pipe was sufficient because it had a low shear fracture energy, because the shelf in that ductile brittle transition was at a low level. And as I say, it's related to impurities, to sulfur and things that were in the steel. These steels were then called dirty steels. They were pretty clean actually by old standards, but they had a lot more of these inclusions in than the conventional pipeline steels. So if you buy steel from a supplier that meets the specification, you've got to be careful that the specification covers things like these inclusions and things. So that's why we tend to put a fracture toughness number in the specification as well as a strength, because the inclusions are so small in volume fraction that they make little or no difference to the basic static mechanical strength of the system. But for fracture, they make a huge difference. So, of course, you need a convenient test to make sure that your material will pass this, and the Sharpie V-notch test, or the Sharpie test, which can easily be correlated with full-scale fracture propagation tests on pipes, has been used as a sort of way to say, you know, we need this amount of Sharpie energy from this simple test. And a Sharpie test takes about 10 seconds to do. The making of the sample takes a bit longer, but it's a very easy test, and because it's easy, it's quite reliable to use for development processes and quality monitoring. So the Sharpie test that is used is a standard size test piece. You can also use half size test pieces or third size test pieces depending on the wall thickness of the pipe. So this has to be cut out of the wall thickness with the notch aligned in the longitudinal direction so that you can get where the effect of the hoop stresses are. So it's a 10 millimeter square bar, 55 millimeters long, with a 2 millimeter deep V notch cut into it. And you can buy from most suppliers special cutters that are designed to produce the geometry of the notch that you need. So, you know, standard workshop equipment can be used to make these samples. In the Sharpie test, there's a support which is 40 millimetres apart, and a swinging pendulum comes and hits the back of the sample to provide the energy. What normally happens is you lift it up to a certain height, there's a certain stored potential energy, you swing it down with no sample in the way, and you see how far it goes up, and that's the losses just from the bearings in the machine, and you can set that. And then when you put the sample in the way and it breaks, some of that potential energy is absorbed in breaking the sample, so it doesn't swing up quite so high. And by seeing how far it swings, you can therefore work out how much energy has been absorbed by the sample. It's a very, very simple test. So it looks a bit like this. So you have a hammer, and that hammer's got a funny shape because you have to make sure it captures the sample and it doesn't bounce the sample out of the holder. The sample sits here on the anvil. This comes down and it swings through, and you can see at the end of the swing it's not gone up to the original height, so it's absorbed some energy. And what you're trying to do is that sort of bending test. It's a high-speed bending test with a notch on the tensile side. So again, as I said, where possible, you take the Sharpie specimen in a circumferential direction so that the notch and the fracture propagates in the longitudinal direction for the pipe, because that's what happens in real life. You can't always do that. If the pipe is too thin, walled, then you may not be able to. The thickness of that sample is less than the full pipe wall thickness. So that means that if there are problems with defects and non-uniform composition across the wall thickness of your pipe, which there often are, the surfaces are different from the bulk, then you'll have to do some experiments to correlate a full-scale pipe test with a Sharpie test. And many of the companies have done those correlations, and they'll have a simple equation that relates Sharpie to the real life performance. Those performance tests are very expensive, so you want to make sure that you do as little of those as you can to prove that the Sharpie test is going to be right for you. And after doing that, recommended Sharpie levels have been tabulated in the pipe standards. So we've got a strength criteria, and we've also got a toughness criteria in the standards that the material has to meet. Now, of course, these are all things that you can do with any composition of steel you like. So the standard specification does not fix the composition of the steel, it just fixes the properties that you need. So as long as you can achieve those properties and the full mix, including the mechanical strength and the impact toughness, then you could use anything to make the steel for a pipeline. So you have to be careful when you look at specifications that they are performance specifications, and therefore if you pick up steel from one manufacturer and steel from another manufacturer, they aren't necessarily the same. And steel from one manufacturer 1 year might not be the same as steel from the same manufacturer to the same specification another year. And that's not such of a problem when you're dealing with these easily quantifiable tests like strength tests and toughness tests. But if you're going to weld those materials, sometimes the welding procedures will change because the steels are no longer identical, and you have to do some qualification tests. The other thing that you need to bear in mind, of course, is that these steels undergo a ductile brittle transition, and when you change the composition of the steel, you change the temperature at which there's a transition between ductile and brittle. So if you just specify a Sharpie energy, you've got to be careful that that applies at the lowest design temperature for your particular asset. So normally we specify a minimum design temperature of 0 degrees C, for instance, for buried gas pipelines in the UK. If you're in the Trans-Canada pipeline where the outside temperature is -20, you'll be using a different minimum design temperature because that's not what the normal consideration is. And if you're putting a pipe in the Middle East in the desert and you're not burying it, again you probably use a lower design temperature because the nighttime temperatures can be very, very low under certain conditions. So you have to know what your local design conditions are to set the minimum temperature, because you need to know what the brittle behaviour is going to be like in these cases. So what you see here are Sharpie tests, and they don't look too different from the drop weight tear test results. This is a brittle failure at low temperature. This is a mixed failure with a brittle piece here and a ductile piece here, and the top one is a fully ductile failure. So we have again a lower shelf energy and an upper shelf energy associated with the transition from brittle behaviour at low temperature to ductile behaviour at high temperature. So rather, in a Sharpie test, rather than looking at the surface and just saying there's 20% brittle and 80% ductile, you have now an energy from that system, and that energy can be plotted directly on a curve, so there's a number that you can compare. And it's a little bit less subjective, therefore, than the drop weight tear test. Transition temperature, 50% crystallinity, halfway between the lower shelf and the upper shelf. So half ductile, half brittle. So when we talk about a ductile brittle transition temperature, we're going from something which is predominantly ductile to predominantly brittle. Doesn't mean to say there will be no ductile behaviour below that temperature, just that it's 50-50. So you go and look at the standards. So this is the EN standard, and you've got a minimum impact energy in joules for original diameters of the outside diameters of the pipe less than 1.43 meters, and wall thickness less than 25 millimeters. So you start to see that you get different tables with slightly different conditions. You'll see the values for full-size test pieces. And you've got two things here. You've got the average value to start off with, and in brackets you've got the minimum value. And what you can see is as we go to the higher strength steels, as we go down the steel grades here, so that 555 is the X65 equivalent across here, you can see that the average value minus the minimum value is probably about 10-15 units or something like that. It's smaller at the other end. However, it's a bigger proportion of the total energy at the ductile end. So you've got this this awkward position that you've got. So what you see here is a range of values that you can use in design, and then of course you've got to take into consideration that these things are going to be welded. So requirement 2 here says weld seam requirements, and it's the weld seam requirements are similar to the requirements that you get for a low strength steel. So you hope that the weld is more ductile than the higher strength steels that you've got in these particular cases here. So you've got these tables of data. You then use that as part of the specification for the metals that you order. Of course, you have to do full-scale testing, and you can't avoid full-scale testing to qualify new materials and to make sure that the toughness is correct. So this is a test where some sections of pipe are being welded together in a trench in a place called Spade Adam, which is not too far from here. It go out along Hadrian's Wall towards Carlisle, and you'll pass the signs to it on the way. Spade Adam is a military base, and often these tests happen in military bases because you blow things up. So you have a section of pipe here, and end caps can be welded on, a trench can be made. You can match the sort of conditions that you've got for real case. You can put a defect in, you can apply the stress, and you can watch the explosion when this happens. And then you can go and look at the pipe and see if it did what you thought. You can measure, therefore, crack propagation, and you can measure the damage caused by deliberate explosions in a controlled case in a field in the middle of nowhere where you're not going to hurt anybody. It's the second loudest thing I've ever heard, one of these going off. the loudest thing was a nuclear transport train crashing into a brick wall at 40 miles an hour, which was incredibly noisy. So, for seam welded pipe, weld metal toughness is controlled by means of a Sharpie test. Now, of course, the weld, as if you didn't already know, we'll talk about later, the weld consists of the weld metal that's deposited, and that's the thing that tends to be tested with Sharpie. But either side of the weld, the steel has gone through a heat cycle which changes its microstructures, and these things are called heat-affected zones. And the heat-affected zone, or HAZ, as you can see there, isn't usually measured because it changes depending on where you are in the pipe and the conditions that you've got and things like that. It's usually assumed that if the welding procedure is good, that the heat-affected zone isn't going to be a disaster if it changes its properties. But just to make that sure that that's not going to be a problem, when you've got a segment of pipe that's being welded in the field, it might have a longitudinal weld along the pipe to make it, you make sure that that weld is staggered. It doesn't match up to the weld on the next piece of pipe and the next piece of pipe. So if a crack starts in the weld or starts in the heat affected zone, it will run along through that one section of pipe until it gets to the next pipe, which is at a different orientation, and then it will try to crack the pipe base metal itself. So then, you hope, you expect that you have got a failure which will only occur in one or two pipe segments and not will run on and on and on. So don't line all your welds up. That's the message. Yep.
So would you generally expect the toughness in the HAZ to be lower or higher than that in the weld material? Or
Yes.
Similar order? Yeah. Yes.
It could be lower, it could be higher, it could be similar order. You don't know. We'll talk a bit more about this. If the cooling rates in the HAZ are very high, which they are, you can get martensite formed, which is brittle, toughness will go down. If the cooling rate is a bit slower than that, it isn't brittle, you get smaller grain size, the toughness goes up. So you've got two competing mechanisms, and you can get anything from one to the other. So if you do it properly, the HAZ toughness should be about the same as the metal toughness.
So if you were retrospectively, using Sharpie testing to retrospectively prove weld quality,
Yeah.
for example, would you, sounds like a toughness testing in the HAZ wouldn't necessarily be useful, or?
It can be useful for two reasons. First of all, if you've got a welding procedure that you want to check for a repair weld, you need to know what you're starting off with in the material that's there, because the repair weld may have overlapping heat affected zones, or it may be that you have an area where there is a repair weld and then there's a new weld next to it. And anywhere where you get different types of procedure close to each other, that can cause issues. Secondly, welding consumables introduce more elements into the weld pool, and some of those over a period of time can end up diffusing into the heat affected zone, and you might find that there is an influence from that. The real problem with it is getting your Sharpie test with the notch in the heat affected zone, and so there's a bigger variability on where the notch gets positioned than actually the variability that it would cause. So I've had student projects, and it's Pipeline MSc, trying to do a set of Sharpies through a weld to look at these heat-affected zone effects. And because your weld isn't vertical, it's this sort of shape, you've got different amounts of weld being sampled by each case. The tip of the Sharpie is not always at the same position with respect to the material testing. You can get almost any result just by moving things a little bit. So it would be a really good, if we had a localized test, it would be really good to do it, but we don't. So when there isn't a good test, people don't tend to do it. Doesn't mean to say it wouldn't necessarily give you some useful information if it could be done. Pipeline fittings, so bends, T-pieces, that sort of thing, generally have a greater wall thickness than line pipe. And they're fewer than number, and they're generally something that you can look at in a little bit more detail in the factory before, so you can look for defects, do non-destructive testing and things like that. So a simple Sharpie test is sometimes specified on the material just to make sure that the crack initiation doesn't take place within that volume. So you specify just a Sharpie test for initiation. You don't worry too much about crack propagation. In fact, some people assume that a fitting with a heavier wall thickness will stop the crack propagation because the stresses will drop in that anyway. So they're almost put in as crack arresters every now and again. The Sharpie test, though, is there because of the material quality, and we don't want to make sure there's no sulfur contents are reasonable and things like that. So a long-running fracture in a subsea pipeline is very unlikely to happen because the hydrostatic pressure from around is actually acting to close up the cracks. And therefore we don't tend to worry so much about toughness for the subsea pipe materials, which seems a bit strange, but actually that's one case where the external conditions are working in our favour. So again, you want to check on the basic material properties, use a Sharpie test, but we don't tend to specify drop weight tear tests and things like that because that's not an issue that has come up.
Is that follicular specific depth, or is it?
I have not seen anybody talking about this when the depth is more than about 100 metres, but yes, I think there is. If you're in the splash zone and you're in the shallow depths, then there are all sorts of other questions, and I'm sure the specifications are much more complicated in that case. But for the basic pipe material on the seabed, generally not an issue. Again, we do the Sharpie test for material quality, and that should cover everything. That's the idea, I think. Okay. Right. So how can we reduce the possibilities of fracture? Well, if the pipeline is operating at less than 30% of specified minimum yield stress, then the chances of getting a brittle fracture are virtually zero. So one way to actually deal with these toughness issues, if you suspect them, is just to downrate the pressure in the pipe. And that is often the case for assets that have been around for some time, and there's a level where you do the NDT and things like that, and then you keep these things running at a low pressure just to get as much out of them as you can and use them as backup systems, secondary pipelines and things like that, because there's no real risk of brittle fracture. Now that's for older pipe assets. Obviously, if you've replaced it with a newer pipe asset, there's a less risk of the brittle fracture anyway, and it's probably not something that you're going to worry about too much. 50% SMYS, the ductile fractures probably won't operate. So you can see, again, down rating is a way to deal with some of these fracture issues if you're worried about them. And that's when the non-destructive evaluation comes in, which we'll talk about later on in the course. So as I say, if there's a fracture problem with an old pipe, if there's a potential for a crack or a section that's been cracked and repaired, and you're worried about the whole asset, then you might just downrate the whole thing. And that effectively reduces the design factor in the calculations, which effectively means that the asset can run on for a long time. And there are some ancient pipes running that have been in service for 40, 50, 60 years, which are operating at something like 10 to 15% of their original design capacity. But they're still there because they, for instance, provide supplies to hard to get at parts where the replacement cost is very expensive, and they can be used because the demand for gas for that particular location is relatively low. So you be careful, because you can find that there are some very old and not very good materials in service and you can't switch up the pressure just to deal with excess supply. So sometimes in this country we'll get new towns, new factories, new gas-fired power stations built, and then people have to look at the assets that they've got for supply to those areas and make sure that the pressures are possible for all of the assets. Okay, let's move on to welding. Pipe is a simple geometry. It's a tube. Circular cross section. We don't have any funny square pipes in this country. Stick the two pipes end to end and weld them. It's easy, isn't it? Probably the easiest type of welding, apart from putting two things that are much smaller than a pipe together. Well, in principle, yes, but in practice, no. So weldability, the ability of someone to make a decent weld, a good quality weld that does what it says, is much more difficult. I'm no welder. I know how to switch on a welding torch. I know how to make a joint. I can do a pipe weld. Anything I do would not pass in the field whatsoever because I am not that good. I might be able to teach you about welding in a laboratory class, but not about how to be a welder. Part of the reason for that is I learned to weld on a desk or on a bench in a workshop with ideal conditions around. It was warm, it was well ventilated, we had the right extract and everything there, and I had a small thing in front of me to weld and the torch to hand, nice umbilical to the MIG welding system. Very easy to do. Now you're doing exactly the same weld, exactly the same conditions, but you're welding it in a tent, on a field, when it's raining outside, you're cold, you're wearing protective equipment and things like that, and it's not the same. And it's harder, and it's more difficult, and you need a certain level of manual skill. When you go out on site, you find welding is a young person's or young man's job, generally. I mean, there are female welders, but they're much smaller numbers than the men on site. Because as you get older, it becomes more difficult to manipulate things, your strength goes, your hand-eye coordination is more difficult. So you actually have to qualify welders, and you have to actually assess their ability to make welds and make sure that they do things properly, and that is quite tricky. So in order to do that, we need to have some way of assessing how easy that weld is to do. We call this weldability. And unlike strength and toughness, it doesn't have a number associated with it. It's a more difficult parameter to define. And one definition here is the ability of a pipe or fitting to be welded using welding procedures which are economic for site pipeline construction without the formation of cracking or excess hardness. So how do you put a number on that? Well, you can't. So this is the most difficult part of defining these sorts of orders. It's getting something with sufficient weldability that you can guarantee that the welds produced on site are going to be fit for purpose. So we can do something about that. And one of the things we can do is see what happens when you do the welds on site. And here's an example of manual metal arc welding with cellulose coated electrodes. So you can see the weld pass there, you can see a capping pass there, there's a root bead here, so this is a multiple pass weld. In fact, there's several passes in the fill here. And we've got some penetration issues here. We've got penetration bead. Look at this part of the steel and this part of the steel, they don't match up, so there is an alignment issue here, and we've got a change in cross section which leads to stress concentration. And then we've welded with cellulosic electrodes which have not been dried, and hydrogen is produced, and hydrogen makes the steel brittle, and we get hydrogen embrittlement. So this crack comes straight through there from the hydrogen dissolving in the weld pool and then embrittling it as it freezes. So when we're talking about weldability, we have to take these sorts of things into consideration. These are cracks, in this case, that have come because of the welding process that we've done. They were not an intrinsic property of the steel to start off with. The hydrogen has come from the dampness in the air, and that has then caused the problems. So hydrogen cracking is the biggest problem, probably, with field welding. Tends to occur in the heat-affected zones. As you can see here, the light blue areas are the heat-affected zones. The crack might start at the weld metal. It tends to start at the toe of the weld. So this is the fillet weld of the toe, right at the edge. And the crack you can see running in there, and it's running underneath. And there's another one here where there's a change in cross-section, so there's stress concentration. The toe of the weld here has more defects in it than the bulk of the weld, and that's why that tends to be a starting point. In a butt weld, again near the penetration bead, this is a case here where we got lack of penetration on one side, so again you can get the crack coming in there. And for hydrogen cracking to occur, we need a source of hydrogen, and that's often water. We need a susceptible microstructure, and so some of the martensite structures I talked about a little while ago are more susceptible than the basic ferritic steel structure. And we need tensile stress, either residual stress or applied stress. Now if you consider this butt weld here, if you clamped either end of the steel and you welded it, you're clamping it so it's all flat, what's happening to the weld metal? It's deposited at a very high temperature, it cools down to room temperature. The steel therefore contracts because its thermal expansion is being driven in the opposite direction. If you clamp the material at either side and you allow it to contract, you're putting the weld metal and the heat affected zone into a state of tensile stress just from the mechanics of welding. So that's the residual stress component, if you like. And the applied stress is you've got to pick these pipes up and you want to move them around, so there will be bending stresses and other stresses applied. So the reason this is sometimes called cold cracking in hydrogen is that it happens at the end of the welding process. It happens when things are cold. It happens when things are being moved around after the welding process is complete. Hardness is important in these cases. The harder the material, the more brittle it is. So if we put a hardness test in, this is a diamond pyramid pushed into the surface under a fixed load. The bigger this is, the softer it is. The smaller it is, the harder it is. So there's the parent metal, heat affected zone, more heat affected zone, and then the weld metal. Nice big impression, so soft weld metal, reasonably big impressions here and in this part of the heat affected zone. But in this part of the heat affected zone, right next to the weld bead, that impression is smaller, so that has a higher hardness. And this is where phases like martensite form, and this is where brittleness is most likely to occur. So you will most likely see cracks, if you do get them in welding, in the heat affected zone next to the weld pool. Well, that's where they'll start. So it's not the weld metal that necessarily is the problem. It's the change in microstructure that you put the steel through when you actually make the weld. And that depends on chemistry, it depends on the size and shape, it depends on fittings, it depends on everything, you know. So that's why we do quite a lot of measurements of welds, and then we cut them open and we have a look at the microstructure changes and we see how the mechanical properties change. And we can do this local mechanical test with a hardness impression that will give us an indication of what's going on. And you can even polish the surface of a weld and use a portable hardness tester to actually monitor the heat affected zone hardness if you really need to. So what do we want to be able to do to get a good material for welding? Over the years, we have achieved more and more weldable constructional steels by actually reducing the amount of carbon, and in particular the amount of carbon and manganese, in the steels. So you can look at that in terms of carbon equivalent here, which is carbon plus manganese divided by 6. We'll talk later on about different carbon equivalent equations. But basically, to stop forming brittle phases like martensite, we want to effectively reduce the carbon content and the alloying element content of the steels to make them more weldable. And constructional steels have undergone quite a change over the years. This is between 69 and 78, but the same thing has gone on since then. So the carbon equivalent has come down for the same X60 specification. And weldability has improved across that period because we've cut the carbon down and we've made it less likely that these brittle phases will form. So we have, over a period, improved the material that meets the same specification. So this is a point I was making earlier on. Just because you see X60 as a specification doesn't mean to say the composition of the steel will be the same. What meets an X60 specification today is completely different to what it was like even 20 years ago. So what affects weldability there then? There's a load of factors. Increasing the carbon equivalent, increasing the carbon and alloy content for the steel. Every alloying element, nickel, chromium, manganese, molybdenum, all that sort of thing, everything, with the exception of cobalt, will decrease the weldability. And it'll increase the cost of the steel. So if you you don't really want to put them in anyway, but anything that you add is going to make things more difficult. Martensite forms by heating up to an austenite temperature range, about 700-800 degrees C, 900, and then cooling very rapidly. So if you increase the wall thickness of the pipe, there's more metal to conduct the heat away. So increasing the wall thickness, the weldability goes down. Similarly, if you increase the diameter of the pipe, there's more metal in the pipe, the weldability goes down. If you increase the grade, so it starts off with a higher strength, there's more cold work been done to actually make the pipe grades with these higher grades. They're more difficult to maintain the microstructure, so the weldability goes down. If you increase an individual length of pipe from 12 to 18 metres as delivered, there's more metal to conduct the heat away, the weldability goes down. And if you decrease the ambient temperature, so you're welding in a Scottish field in the middle of winter, the weldability goes down. So anything you do to increase productivity and to make the process look nice and simpler and easier tends to make it more difficult to weld. And so you have to think about these things. So carbon equivalent is the way that people have an assessment of this. So carbon equivalent formulae take the most common alloying elements in the steel and factor them according to their effect on weldability. I've said there, they were originally developed by the steel industry to look at the ability of the steels to make martensite. So hardenability became weldability when the welding engineers got hold of it. It's the same idea. It's what makes the steel hard and brittle. So the steel industry did it for developing tools, and the welding industry's done it for developing constructional steels. And so it's a different use of the same ideas. So the International Welding Institute equation is the most common formula. So the carbon equivalent is the percent of carbon plus the percent of manganese over 6, that was on that diagram, plus the percent of chromium, molybdenum and vanadium over 5, plus the percent of nickel and copper over 15. Those are the main steel alloying elements, and you can see that everything that you do has an effect. So a typical constructional steel might have a small amount of nickel, molybdenum, manganese in it. So the basic carbon content is 0.2%, but the carbon equivalent is about 0.5%. And it's much harder to weld than you think because of all these other elements. And the killer one really is manganese. because that's added in the primary steelworks. So when we talk about carbon steel, what we should really say is carbon manganese steel, because every steel has manganese in it. It's a deoxidant and it deals with the sulfur in the steel, but it affects the weldability. And so you need to know that the manganese content. There are other variations. PCM equation here. This takes into consideration some other elements. Silicon, which is added as another deoxidant, and aluminium. And it's got vanadium, which is added for carbide formations for some of the higher grade steels. So it's more of a useful formulation for some of the newer steels. And it's mainly applicable to the lowest carbon steels of most recent generations. So the IIW formula tends to be used more widely because most constructional steels are not less than 0.12% carbon. But if you're making a car body or something, that's the sort of steel that you're going to use. And what you can do is set a limit on the maximum carbon equivalent or the maximum PCM value for a particular project. So then different steels, you can plug the numbers in from the composition into these formulae, get an overall carbon equivalent and compare that to a limit that's been set. These are metallurgical numbers, so they're not atomic percent, they're weight percent. All metallurgists work in percent by weight. So any physicists and things around who want this done in percentage of atoms, go away and think again, because these all came from metallurgists. Weight percent is everything. So these numbers, when I say percent manganese, that's the percent by weight of manganese in the alloy. Does that tell you everything you need to know about weldability? No. It's a rough guide. But if you're changing from one material to another, it's the first thing to do, just to check that it meets the specification. Usually you have to do some sort of testing. So what do we got for weldability tests? Small scale tests, intermediate scale tests, full scale tests. So small scale test, you just put two pieces together in a restrained jig, weld them, and see if we get cracks. Very simple tests. You can get some standard laboratory tests like implant tests, some Y-groove tests. I'll show you a picture of these in a second. But they're all done in the lab. And the idea is to get a procedure which you think you're going to work with. So the Y-groove test, you can see here, you've cut a V-shaped groove in half, and then the grooves are in the same direction in here, so it looks like a Y shape. You put some constraining welds on either side to be full, and then you weld in this patch here, and you look for cracking in the bottom here. Implant test, you have this implant, you stick it in, you weld across, and then you've got something you can pull out to measure the mechanical properties of the weld test. So these are standard tests. You can look up the procedures. They're in the standards and things like that. They can only tell you that the welding procedure made a good weld or a bad weld in the lab. They don't tell you what's happening outside. Intermediate tests you have to do, that's full girth welds between pipe pups. A pipe pup is a short section of pipe. And this is often what you do for welder training. And then you can cut that pipe section up and you can do hardness tests, cracking tests, mechanical tests, and get some indication of how it varies from welder to welder or from position to position. And you need to do those tests. And then you finish off with full scale tests, full girth welds between full pipe lengths, simulated site conditions, everything that you wanted. So here's a full scale test in operation. This is to test the craning of a pipe that's been partially welded into a trench. So you've got a weld here and the root bead has been completed, but none of the capping passes or fill passes have been done. Then that weld is being picked up by this crane. The whole thing will be bent and stressed, and it will be moved and put down as if it was being craned into a trench. And that's done for cracking testing by non-destructive testing before and after, just to check that no cracks form. So if somebody makes a mistake and starts to put things into trenches before they're finished, you can check that that's going to work. So these for full-scale tests really match site conditions as much as you can. Nearly finished. So just for conclusions on design, strength is not easy to measure accurately. There's a spread of properties, so we go for the specified minimum yield stress. Toughness, we can measure for brittle and ductile fracture propagation. We can use drop weight tests for brittle and Sharpie tests for ductile fracture, and we use a Sharpie test for measuring fittings. And weldability, carbon equivalent formulae are often used to assess different materials, but they're only a guideline. They don't tell you about the welding procedures used and how that affects things. So you have to do tests. Small-scale tests in the lab can prove a procedure for trial, and then it has to be tried on intermediate scale tests on pipe pups and things like that to make sure that it's a practical test that the welders can do reliably and give you good results. And finally, you have to do full-scale tests, because without that you can't guarantee that the welding procedures are going to be suitable, and you therefore need to qualify every step of the welding procedure, not just the depositing of metal, but the handling of the pipes and things once that has been done. And that is the end of the introduction, which I've raced through to get it done just in time. So you've now got a couple of weeks where there is no materials of fabrication, because the pipeline engineers have their introductory modules elsewhere. When you come back, what we're going to do is take some of these things we've heard about here and go in even more detail. We'll talk about making steel, we'll talk about turning steel into plate, turning plate into pipe, joining pipe together to make the pipeline, and how you look at the defects, how you guarantee that that pipe is going to work, and what you have to do to introduce new materials into the industry. And that will happen after you've had your couple of weeks of pipeline introductory lectures. Okay.
Are we going to run these tests?
You'll look at the results of some of the tests. If you do a project, you might do some of the tests themselves, but it takes a long time to make the samples, and generally we find that it's better just to see what comes from there. You're doing as a lab class, you'll actually get a chance to look at some of the metallography and look at the samples that have been cut from welds and try to understand the weld microstructures and things like that. And we'll do some simple stress calculations for those that are not used to it. But actually doing the mechanical test, we can show you one, but that we'll leave to previously done tests.
For the small-scale weldability, weldability tests, would they be done with pre- and post-weld heat treatments, or would they be?
Yes, that they can be. They can be used to actually specify what those pre and post weld heat treatments have to be. So you always try things out with a small scale test, and then when you think you've got something that works, then you'll do the larger scale tests to make sure that it works. Yeah, pipe, you just cut the end off the pipe. It might be about this wide, this sort of size. And then you can cut a pipe into lots and lots of sections. So a welding team can take one 12-metre pipe and have 20 pipe pups, which they can then try. Okay.
It's our last weekend, so we need to make the most of it. Yeah. Are you going to Fabrications? Yeah, it's not much. It's, you get it in different price time intervals, so you pick up 15 minutes, half an hour. But I don't know. I only got there in May. As for tomorrow, we all need to meet. It's our last weekend, you know. So we need to make them well, we're going to leave for food and then those who want to stay to party and drink, we go out.
오는데